Now we're going to take a look at what happens with ideal gases. It's really hard when you see a bunch of problems like this to figure out, okay, which which law do I use? Do I use combined gas? Do I use ideal gases or whatever? Remember, start all these problems in the same way. P1, V1, T2, P2, V2, T1. Okay, let's just see what you have. So let's take a look at number 2 here. What is the temperature? Okay, well, temperature. All right, I don't know what the temperature is. Temperature is always in Kelvin, though. Of a gas of 6.50 moles. Oh, wait a minute. I have an amount here. I have an amount of a gas. This has nothing to do with any of this. Okay, it's related to pressure. I see temperature. I see volume. But I have an amount of a gas in terms of moles. Think Pivnert. Pressure and volume is a function of the product of the moles and of a gas. So this is pressure. This needs to be in kilopascals. The volume needs to be in liters. I can't emphasize that enough. You will most often be given milliliters. You have to convert it to liters. Same thing as cubic decimeters. Okay, a liter and cubic decimeters is the same thing. This N stands for moles. Moles of a gas. Okay, R is a constant. If you are using liters and moles and kilopascals and Kelvin, this constant number is 8.31. And then temperature, as always with gases, is going to be in Kelvin. Okay, so amount of a substance. So I can automatically take a look at this. I'm analyzing the gas in terms of what do I know about it, rather than changing the conditions. I see the temperature we don't know, but that's going to be in Kelvin. With 6.50 moles, okay, 6.50 moles of a gas, we see that we have 55.6 kilopascals. Yes, that is a pressure, and it's in the units that I need. I don't have millimeters of mercury. I can use that number right away. And we have an 85-liter container. Up there, it's in liters, so my volume is 85.0. Don't forget about sig figs here. So PV equals nRT, 55.6 times 85.0 equals 6.50 times 8.31. Don't forget about your R value. Okay, and then we're going to solve for T. So PV over NR equals T. Okay, so just kind of solve it that way. We can look at number 4, and we're trying to figure out moles. Okay, so solve for N. Here's my V, here's my P, it's in kilopascal, so I'm good. Here's my T, and it's in Kelvin. Notice the V is in liters, so PV equals nRT. I'm solving for N, so PV equals N equals PV over RT. Okay, so nice and easy there. What size container? This is looking at volume. When I say size, that's going to be in liters. We see moles and so on. Now here, number 6 is a little bit trickier because we see 2.67 grams. We're not in terms of the ideal gas law yet. We're dealing with grams, not moles. So keep your head about you. We still have PV equals nRT. We just have to convert 2.67 grams of oxygen. It's diatomic, and get that into moles of oxygen. Okay, 1 mole is 32 grams, not 16. Okay, that's your N value. Here's STP, so my T value is going to be 273, and my P value is going to be 101.3 kilopascals, not 760. That's millimeters of mercury. Okay, so it's got to be in kilopascals. Use 101.3. Solve for V. Okay, pretty much the same thing in this one. You're going to solve for N, and then we convert your moles of sulfur dioxide, SO2, into grams. Okay, so that's nice and easy. As we take a look, now all of a sudden we see down at number 11. Okay, this is a combined gas law problem. Okay, combined gas law says 159 milliliters of a gas is collected at -10. Okay, so I see my pressure, my volume. I don't know whether to use it at this point. Just from reading that, I don't know if this is ideal or combined gas law. So I'm going to play it safe. I'm just going to convert this to 0.159 milliliters. You're never wrong converting to liters. My temperature is going to be -10 degrees Celsius. Add 273 to that, and I get 263 Kelvin. Pressure is going to be 109 kilopascals. That's in the units I need, so no problem. What is the final temperature? Oh, wait a minute. This is my T1. This is my V1. This is my P1. I want to know what my T2 is. All of a sudden, we are changing the conditions. That tells me I'm in combined gas law. We're going to compress it to 15.9. V2 is 15.9 milliliters. Oh, wait a minute. I can leave it in milliliters if I wanted, but my V1 is in liters. I was playing it safe, and I guess I got caught, huh? So I'm going to do 0.0159 liters. Get the units to the same. So I'm going to get my volume actually smaller, aren't I? If my volume goes down, my temperature is going to go down. Okay? So that's one thing that I can look at. Another thing, we see also pressure, though. My P2 is going to go to 230. What was my initial? My initial was 109. So my pressure is going to go up. I'm squeezing this gas. So as pressure goes up, temperature goes up. So I've got two different things going on there. My volume is going down, my pressure going up. Solve for T2. Okay, this is going up by double, but this is going down by a factor of 10. So, kind of an interesting little problem. Take a look at these problems, and also number 15 is not that hard of a problem. Gas effusion just says which one moves faster. Carbon dioxide, which is CO2, well, that's 12 plus 32. Its mass is going to be 44 grams per mole. Ammonia is NH3, that's 14 plus 3, that's 17. Now, technically, you're supposed to take the square root of the masses and you find your effusion rate, your actual rate there. For this chapter, all I'm worried about is which one is going to move or effuse faster, and that's going to be the one that is the lightest. Chunky runs slow. That's right, I said it, and it's going to be on the internet forever. Chunky runs slow. So the faster one, in this case, is easily, hands down, going to be ammonia. Okay, so ideal gas law is just dealing with a snapshot, solve for those variables, and be careful with it. Pretty easy if you really think about it. You can bypass the 8.31 and all that if you take a combined gas law, you take those gases, you put it into standard conditions. Okay, so I'm just going to pause and let you think about this. My 8.31 comes from, you take the gas at the conditions it's at, you change those conditions to standard pressure and temperature. You're going to get a new volume using 22.4 liters per mole. Okay, use that then to solve for moles. There's your N value. So that's where that 8.31 is, and really where the combined gas law and ideal gas law overlap. If you're only given one set, well, what would that gas be at standard? And then you can convert that volume into moles using your 22.4. So don't, if one way works best for you, you don't actually have to use the ideal gas law at all. You just have to change the conditions so you can use your 22.4. Okay, good luck, and that's pretty much it for the gas laws. You know all of the ins and outs of it with combined gas law and ideal gas law.